Hi, welcome back to the channel. So today we're diving deep into MCP, the model context protocol that's revolutionizing AI-driven systems. I will show you how to build a robust MCP server from scratch, architect multiple context-aware features, seamlessly connect an MCP client that understands plain English requests, transform them into SQL queries, execute them on your database, and then return polished natural language response. So you can find the link to the GitHub repository in the description below, and be sure to check it out and give it a start to support the project. And by the end of this tutorial, you will have a fully functional MCP ecosystem server, client, AI assistant that are all working together to bridge human intent and data access. So I will teach you how to integrate the following core feature in an MCP. So we will see communication protocol, so we will discover the RESTful API endpoints, but also integrate the WebSocket communication for persistent and bidirectional interaction, capability management, prompt registration, resource, and also how to execute and access. API session management, we will integrate API key authentication, quota management, and WebSocket session management, including initialization and cycle, and also some core server functionalities like health checks, server informations, listing capabilities, calling, executing capabilities, asynchronous operation, structure logging, dynamic request validation, and application lifespan management for resource initialization cleanup. What actually is the model context protocol? MCP is an open standard that makes it effortless to forge secure bidirectional bridges between your data sources and AI-powered applications. In its core, MCP lets you like any data set where there is a Google Drive, Slack, Postgres, or just a custom system through a server implementation, and then build AI clients that connect to those servers to fetch and act on contextual information. So by standardizing how AI agents retrieve and maintain context across disparate tools, MCP simplifies the creation of powerful, multi-step workflow agents that chain together the lookups, transformations, and actions without reinventing connectors for each new integration. This not only accelerates development, but also ensure your AI-driven systems stay coherent, scalable, and secure as they evolve. So let's explore the code and let's develop the system from scratch. So let's start. As you can see here on the repo, the project is divided into main folder, the server, and the client. We will see the client. Now let's develop the server part. So now we are focusing on two key files, that is base session and server session. In a nutshell, these files are responsible for managing individual WebSocket communication sessions between a client, like a web browser or another application, and our MCP server. So when a client connects to the server via WebSocket, a session is established. So these Python scripts define the classes and the logic that handle everything for that specific connection, like initial handshake, receiving messages, authentication and quotas, processing a request, dispatching to handlers. So base session provide the foundational building blocks, and server session builds upon that foundation to implement the specific application logic. Let's explore the code. We start with base session, as you can see here. The first class that we can see here is the request responder. So think of a request responder as a helper object that takes care of a single incoming request from a client and make it easy to send a reply. Okay, so the purpose is to wrap an incoming request and provide convenient methods to send back a successful response. Okay, so we can find trec and tres actually are type variables. They mean that the request responder can be used for various type of requests. The key attributes are request. Type session manager stores the actual request message received from the client. Let's discover here in the protocol types that it includes all the specific types that enter in the session message, discover later one by one. And we have the responded that actually is a flag to keep track if a response has already been sent for this request. We have the stream. This is the pipe or channel used to send message back to the client. NEIO is a library for asynchronous programming. You can see import. We have init. Okay, we have some parameters you can find here. Is the constructor. It's called when you create class, of course. It takes a write stream. Okay, it takes the write stream. That actually is the channel to send data back on, and the session manage the client's request as input and store them. We have enter. These methods allow request to respond to be used with Python with statement, and with responder. Okay, ensure that any setup or cleanup can happen automatically. In this specific class, the exit, as you can see here, doesn't do much automatic error reporting, as errors are handled explicitly by the parts of the code that use the responder. So we have this async function that is respond. This is how you send a successful response. It takes a result, which must be one of the server result types defined in protocol types. So server result type defined here, protocol types, and it includes all this kind of result specifically. So it's going to join union of all the types, and it wrap the result. Okay, it sends this session manager back to the client using await self stream send. Okay, this method, and finally it sets the self responder to true. We have also this other function. This is respond error. This is how you send an error response. It takes an error code. For example, it can be 404 or another error. It creates a types. It creates a types that is server error object, and wraps this error object into a type session manage, as we saw before. Send it back to the client via await self stream send, the same way. Also here it flags as true. So we can see the server error types also here, protocol types, and it includes the code and the message. So it's an integer and a string. Okay, let's discover an important class of this file, that is server session. This is the base class for managing a WebSocket section actually on the server side. With server session, that is another class we will see later, will inherit from this. Okay, so the purpose is to send an initialization response to the client when the session starts. Continuously reads incoming session message object from the client. If the message is a client request, it wraps in a request responder, which we just discussed. Makes this wrapped request available with the asynchronous iterator, that is self-incoming messages, for other parts of the server, like with server session. It handles API, key authentication, and quota checks for incoming requests. So let's start from the init. So the constructor takes some important parameters. The read stream is the channel to receive message from the client. The write stream, the channel to send messages to the client. It options, as we can discover here, we can find types, protocol types. It includes the server name, the server version, capability, the instruction. This is, you can customize as you want. It's just a welcome initialization message. We have the API key that is provided by the client for this session. The key store, an object that manages API keys and their usage quotas. Let's see utilities outpwise we can find here. We also have the app state, a way to pass a shared application state, like database connection pool to the session. So inside the init, we also have a send chain and a receive chain. Actually, will be used by the receive loop to put new request responder object, this internal queue, and also self-incoming messages. These allow the with server session to easily get the next request to handle. So we have the receive loop. This is the heart of the server session. It runs in a loop as long as the WebSocket connection is alive. Okay. At the start, we have the initialization response, this type, using the self-init options, okay, passed during the construction. This response tells the client about the server's name, version, capabilities, and other information. So it sends this wrapped in a session message to the client using await self write stream. Okay. This function, async for message in server and stream, actually pump incoming messages in a loop. This means it waits for messages to arrive from the client one by one. The root, okay, it gets the actual payload from the session message. If it's an instance of initialization request, it ignores, okay, the message from the client after the first one, as the server has already sent its initialization response. So after this, we have the quota check logic. This is a very important section for controlling API usage. Is rate limited request actually is an instance of root and all the other types. It first checks if the incoming message type is one that should be rate limited, one of like a tool call request, help request, and many others. So if self API key, right, and the key store and is a rate limited request, so the quota check only happens if an API key was provided for the session. A case store is configured, and it's a request type that needs checking. So if it's valid, it calls the validate method on the key store. This method typically checks if the API key is valid and if its usage quota is not exceeded. So the increment through part means if the key is valid and with its quota, its usage count is atomically incremented. If it's not valid, if validation fails, it checks again without increment. Await self case store. Okay, this function is to determine if the failure was due to as an invalid key or because the quota was exceeded. And you can find here some error message and try except block. Let's check the wrap client request. Okay. If the quota check passed or wasn't needed, the message is a recognized client request type. If it's an instance, okay, this part, it checks the root of the message is one of the known request types that the server is designed to handle directly, okay, like calling a tool, listing prop, etc. The responder, that is a request responder, is created, giving the right stream so it can send replies and the original client message. So last part, this wrap the request, the responder object, is then sent into the internal channel MSG send. Okay. This makes it available to whatever is reading from self incoming messages, which will be our with server session. Okay. Else it continues. If the message type is not one of these recognized request types, it's currently ignored. So server session acts as a gatekeeper and initial processor. It handles the connection setup, authentication, quota management, and then queues up valid wrapped requests for more specialized handle. So let's analyze the server session PY. Actually, it includes a class that it is with server session. This class actually is the key, is a server session, and it inherits all the capabilities of the server session like a receive loop, incoming messages, and others, and then adds more specific behaviors. Okay. The purpose actually is to take the request and queue it by its parent server session and dispatch them to the correct handlers. If it's a tool call request, call the appropriate tool function. It handles the full lifecycle of RPCs. Actually, it's the remote procedure calls like health checks, info requests, listing tools, prompts, resources, and executing. So we can see the constructor here, create a registry. This is a dictionary mapping tool names to their specifications. Okay, description, input schema, handler function, This comes from the MCP server where tools are registered. We have the prompt registry, similar to the registry, but for prompts. We have also the resource registry, the same, similar, but for a resource. Then we have the read stream, write stream, init options, API key store, and upstate. Okay, these are passed directly to the parent server session, the constructor using super. Okay. Inside init, it stores the tool registry, prompt registry, the resource registry, and all the bare tools, prompts, and resources. Okay. So these bare versions are essentially simplified list of tools, prompts, resources containing only the information safe to send to the client, like name, description, input schema, but excluding the actual Python handler function and internal flags like expect or other. So these are used when a client asks to list available tools. Let's talk about the start dispatching function. This method is typically run as a concurrent task when a session starts. The async responder continuously waits for request responder object to arrive from the incoming messages queue, which is populated by the parent server sessions receive loop. And we have await self-end request. Okay. Here, that it means that for each incoming request wrapped in a responder, it calls handle request to process it. Let's explore handle request that actually is the core of this class. This is main dispatching logic. It figures out what kind of request it received and calls the appropriate method to handle. We have inner here that gets actually the payload from the session managed held by the responder. Actually is using the Python structural pattern matching to determine the type of request. We have different keys. Let's analyze one by one. Tool call request. If it's a request to call a tool, it extracts the tool name and args and calls away self-exec tool. Okay, so actually it is activated to execute the tool. Let's discover the types for tool call request and tool call request params that you can find all here in the protocol types. Here in the tool request we have the method. It's a literal, it's called tools call, and parameters that is name and arguments that are change depending on the tool. We have the prompt call request, similarly called to execute a prompt. We have the resource and also the health request. And info request actually responds with server information, name, version, capability, take from the self-init options. We have also the types tools list request. This case demonstrates sending a progress update to the client. It's really useful when you want, for example, to update the client during a request, sending some message from the backend, like in an AI assistant. You want to show all the reasoning steps in the chat. You can use the process update here to keep the client updated from the backend process. Await annual sleep here is just for demo purpose, and we set just some demo update. And another pause and another update message done preparing here. And yeah, finally it used the responder to send the actual list. This will send directly the list of tools. So now let's discover the execution methods. Let's discover the exec tool. The get tool registry, it looks up the tools details and function scheme from the registry. And it means that if spec is known, it means that the tool doesn't exist. So it sends a 404 error using responder. We have also Pydantic, okay, for parameter validation with a try except block. In this part, it uses tick for data validation libraries. It gets the expected input properties from the tool, from its schema. Params model, actually, it creates a model, dynamically creates a Pydantic model based on the tool's expected input schema. This model actually will be used to validate the arguments provided by the client. Validate Params model actually attempts to create an instance for this dynamic model using the client provided arguments. If the arguments in this part don't match the schema, wrong type, missing required fields, Pydantic will raise a validation error. So we have the context injection. This queries a validated dictionary. It converts the validated parameters into dictionary. This part checks if the tool's handler function expects a context object as its first argument. This is determined when the tool is registered with MCP tool. We will see later in the decorators. Actually, this part creates the context to initialize some resources, base or other resources. This is the call handler, and it calls the actual tool handler function retrieved from spec with validated and possibly context injected. As a result, it handles both regular and async tool function. If the handler is an async function, it awaits its result. We have the reply at the end, so it sends the successful result back to the client wrapped in tool call result. And we have the exception handling. If any error occurs during validation or execution, other than Pydantic validation error, which is coded implicitly by FastAPI for HTTP, but actually needs explicit handling here if not coded by the try except exception. The exception block catches and it for 00 error using the responder. Okay. And exec prompt, this method is structurally identical to exec tool, but it uses the prompt registry and prompt call result. So we are going to analyze because it's the identical. And we also have exec resource. This is slightly different because the resources are identified by URI pattern. And for example, user slash something like this, users. And we have some parameter like user ID, profile. So that's how we identify some resources. And in this part, actually find matching resource and extract parameters. Okay. It iterate through the resource registry items. Okay. In this part, there is a regex. Each resource spec in the registry should have a precompiled regular expression regex pattern generated from its URI pattern. Match. So if it tries to match the requested URI against this regex. If a match is found, extracts the values captured by the regex groups. These are the path parameters values like 1, 2, 3 from the URI. The param names gets the names of the path parameters. The extracted args from URI that creates a dictionary mapping parameters names to their extracted values. And breaks it, stops searching once a match is found. It handled no match in this case. After checking all the registered resources, it sends a 404 error. And we have the last part that is a try catch block. Actually, is a parameter type conversion and validation try except. We have this part matched spec path parameter schema. Actually, it's the schema definition for the path parameters. It iterates through the extracted args for each name and value string. It lookups prop details, and it tries to convert value string to the correct type, if it's int, float, bool, string, based on the props details. Okay. If the conversion fails, anyway, it sends back their message. And we have the same logic. This is the context injection that is the same. Okay. It helps us to initialize the resource and make them ready inside the tools. It's the same of the exec tool, so we are not going to apply here. The call handler is the same, and also the reply. As you can see, the with server session is the specialized engine for our MCP server WebSocket interaction. It leverages the general message handling and authentication capability of server session and adds the specific logic to know about the registered tools, correctly parse the requests, validate inputs, inject the context like database access, execute the code, manage both sync or async function to package and send back the result on errors or format the client's expect. This layered approach makes the code modular and easier to understand and maintain. The use of an AIO for asynchronous operation allows the server to handle many client connections efficiently without blocking. Pydantic ensure data integrity for requests and responses. So now it's time to analyze the core files, server PY and main PY. Server PY is the engine room This is the heart of the MCP Wiz framework. It defines the MCP Wiz Server class, this right here, which is the engine responsible for allowing you to register your custom tools, prompts, and resources. It allows you to put decorators in main like this to define tools in a really simple and clean way. So this decorator is applied here inside the server PY. Handling incoming HTTP requests to list or call these register items. Managing WebSocket endpoint / MCP for more interactive session-based communication. And taking care of things like request validation, routing, and response format. The main PY is the application blueprint, actually. That is, this file is an example of how to use the MCP Wiz Server framework from server PY. It demonstrates instantiating the server, defining concrete tools like text-to-SQL converter using OpenAI or simple calculator, defining prompt templates for LLMs, data resources, setting up application-specific configuration, and finally running the server so it can start listening for requests. Okay, think of server PY as providing the car, okay, the framework, and main PY as building a specific model of that car with custom features and then driving it. While server PY and main PY are our stars, they rely on few supporting files. Base session and server session. Base session and server session we already discussed that manage the logic. Protocol types, it includes all the types. And context model define how context like request information and shared application resource like a database or connection is passed to your tools and resources. It actually is just some classes here. We will touch on this as they become relevant. For now, let's start with the engine server PY. So that's the core. At the heart of the file, we have MCP Wiz Server class. This is what you instantiate to create your server. This is the constructor. You define the version, title, all your information, and lifespan to known. It initializes a FastAPI application here. FastAPI is a modern and fast web framework for building APIs with Python. And it's what MCP Wiz uses under the hood to handle HTTP requests. These create empty dictionaries, tool registry, prompt registry, and resource registry. These will store the tools, prompts, etc. The lifespan argument is interesting, as we saw before. It's for managing a setup and tear down action for your application, like connect database when the server starts and disconnecting when it stops. We'll see this in action in main PY. Crucially, it calls self-setup route, which we will look at the next. Let's talk about the decorators, registering your functionality, specifically for tool, for prompt, and for resource. How do you tell MCP Wiz Server about your custom function? Through Python decorators. These are special functions that modify or enhance other functions. So the decorators we apply directly over the tool function here in main. It applies the decorator here with server. When you decorate a function with MCP tool, this tool method is in MCP Wiz Server, and this method is called. Okay, it takes your function fn. Okay, it determines the tool's name here. It gets the description either provided or from your function docstring. It generates an input schema here using another helper like schema from signature. This schema defines what arguments your tool expects and their types using Python type hints. This is great for automatic validation and documentation. It offers to the agent, the LLM, all the information in it to select the tools and to execute the tools. It stores all this information, including a wrapper around your function in the handler, into the tool registry. It also checks if your tool function a special CTX context, and which is used to pass in request-specific data or shared application resource. We have the same prompt that we apply with the MCP prompt. Main, we can see a prompt. Here we go. Here, for example, we get a prompt for text translation. It's very similar to MCP tool. It's designed for functions that generate prompt strings, often for interacting with large language model. It registers the prompt function in prompt registry. So let's talk about resource. The parse URI pattern actually is a helper function that we will touch on. It converts this pattern into a regular expression to match incoming URIs and extract parameters names, okay? And is applied here in the decorator. It also generates a schema for these path parameters, and resource handler and its metadata are stored in a resource registry. Another helper is schema for signature here. And this static method actually is quite clear. It uses Python inspect module to look at your function parameters and their type int. It then uses Pydantic's create model and model JSON schema to automatically generate a JSON schema. This schema is used for validating inputs to your tool and prompts and provided API documentation. Let's talk about setup route. This method is where all the web endpoints URLs for your server are defined. Okay, it tells FastAPI what function to call when a client makes a request to a specific URL. We have the HTTP REST, the normal, the standard one. In our demo in the client, we will use the WebSocket, not the endpoint. But if you want to try by yourself, you can also call directly this point or create also new endpoint. And we also have the MCP that initialize that give an endpoint for the WebSocket. So the standard endpoint, we have just some classic like health, info, tools list, prompt, etc. And are used actually to execute your tool, your prompt, resources. And we also have some HTTP invocation helpers, like invoke a tool HTTP. For example, when you want to invoke a tools, you're going to call this helper, actually pass all the name and arguments here and execute the tool and return the response, return the result. And the most important for our case is the WebSocket endpoint / MCP that is here. This is a major feature. Besides standard HTTP, MCP will offer an interactive WebSocket endpoint. So WebSockets allow for two-way persistent communication between the client and the server. Let's see how it works. So, authentication. The first part is the authentication. It first checks for an XAPI key, okay, in the WebSocket connection headers, and validate it against in-memory key store, which is set up in main py. It's a lifespan actually. It also performs a quota check. Any stream and any IO streams create memory object stream, creating memory queues for passing messages between different asynchronous tasks. That is here. And actually the difference between C2S and C2C receiver or sender, for example, C2S send is the session logic will read message from the client via this stream. S2C send, the session logic will send message to the client via this stream. Okay. WS reader, it runs in a loop, reads text messages from the WebSocket. Okay. It tries to parse them as type session manage here and defining protocol types, and if successful, puts them onto the C2S send stream for the session to process. The other side, the WS writer, runs in a loop, takes messages from the S2C receiver stream, which is the session we write to and send them over the WebSocket to the client. And we have with server session that we already analyzed before. We create a session here. This is the command center for WebSocket session, you already know. It's initialized with all the tool prompt resource registries, the communication streams, API key info, and all application state, which all things like DB connection from lifespan. The with server session, which extends server session as we saw before from base session, handles the MCP with protocol over WebSocket. And at the end, we have any IO create task group. This ensure that the reader, writer, and the session task all run concurrently. If one crashes, the others are usually cancelled. At the end, we can find the run method. This simple method uses UVI corn, like in FastAPI Server, to run the FastAPI application that is self-hub. This makes your server listen for incoming HTTP and WebSocket requests on the specified host and port. So, just a recap of the server PY. It provides the MCP Server class. This class acts as a registry for your custom functionalities, tools, prompt, resources, and uses FastAPI to expose them over HTTP and WebSockets. It handles request parsing, validation, uses schema automatically generated from your type hints, routing, and manages the WebSocket communication lifecycle. It's the robust foundation upon which you build your specific MCP with application. Let's deep dive into main PY. This is, as we said before, the car factory. Is where we design and build a specific car model. This is the file, shows how to use MCP with Server from Server PY to create a running application with actual tools and functionalities. So we can find all the imports and setup here to load a variable. Let's talk about lifespan, app lifespan. This is a key part for managing resources that need to be initialized when the server starts and clean it up when it stops, like a database connection. The server context class is a simple custom class, could be a Pydantic model 2, for example, to hold shared resources like the database connection and the key store in this case, but you can also add other resources. This is the asynccontextmanager. This decorator from context lib allows you to create a context manager, code before yield on startup, and code it finally runs on shutdown database setup. We initialize the database here, and it's a classic SQLite base. For our demo purpose, we are going to create a demo here. With init BPY, we are going to create a database for 30 fake samples recorded about people, the first name, last name, and some data, so we can demonstrate how to use the AI agent to transform user in natural language to a text-to-SQL statement, execute the query to the database, and return the results. We also have the in-memory key store. Initialize the key store used in API key out in server PY. In a real application, you'll populate this key store with a valid API keys and their quotas, perhaps loaded from a config file or environment variables. In this case, find file. For example, is your APK and the quota. And you have the app state here. It stores the DB connection and key store directly on the app state, so the FastAPI application state. This makes them accessible through the FastAPI application, including the WebSocket endpoint set up in server, which then passes app state with server session. Yield context is the context. Our server context instance is yield. This dictionary-like object is then available within the lifespan, so the MCP with server can be configured to make this lifespan context accessible to tools, resources that need it via the context. And finally, we have the DB disconnect, ensure that the database connection is closed gracefully when the server shuts down. So, this is where an instance of an MCP server is created. We give it a title, my app, for example. Crucially, we pass our app lifespan function to the lifespan parameter. FastAPI will use this to manage the setup. So in this way, we can use the resource inside the tool or any other part of our main class. And we define some tools. Here I define some tools for our demo. For example, this is the interesting part where this is actually a tool that take a user query, convert to SQL, and execute the query to the database, return back the results. As you can see here, is an asynchronous tool because the DB is asynchronous, so we have to use a wait here. Its string automatically becomes the tool's description. It makes CTX context and text string as input. Context automatically injected by MCP with server if the tool declares. We integrate OpenAI, PIK. It assesses the database here, click from the lifespan context. This is how the tool gets the database connection. It was set up in a lifespan. The context object, CTX, provides a path to lifespan context. This is a dynamic prompt engineering. It fetches the schema of a people table from the database to give the LLM context about database structure. This is crucial because it helps the LLM to generate more accurate SQL. And then there is the LLM call right here. So this is the LLM call. It constructs a detailed prompt and sends it to OpenAI GPT-4o model. So you can use model here to convert the user natural language text into a SQL query. And later we execute the SQL. We execute the SQL here, returns the query result in hand. We have another tool that is just a simple query DB, but we are not going to use in our client demo. It just performs directly a query, so provide the statement on the parameter, directly the SQL statement. We have other just simple tool like add, summarize text. Actually, this is a prompt. Prompts are typically functions that return a string, which can then be sent to LLM. And also some resources, but we are not going to use in our client demo. Resources provide data identified by URI specific. And so here we can also apply some parameters. And that's all. Okay, it's time to discover the client part. And we are going to test our system. We're going to initialize our AI assistant and we check if everything works fine. That's great. Imagine you have a powerful backend server that we already create. That is the MCP server. It offers us some tools that we are going to use now with this from the client. We create this agent that you can request in plain English, find all people who are older than 30 years old and provide their first name, last name, and email address. I already populate the database here, 30 different records. So we're going to query this database with a text-to-SQL strategy. First of all, it understands your request. It asks the MCP server what tools are available. It chooses the right tool. So the LLM selects the best tool for sequence of tools. In this example, it focuses on one from the server list to accomplish your request, and it also figures out what information to pass to that tool. It executes the tool. It asks the MCP server to run the chosen tool with the necessary arguments. It gets the result, receives the raw output from the tool, and gives you at the end a friendly answer. So the LLM then takes this raw output and crafts a conversational, easy to understand response. You can find also another file here, the main basic, that actually you can find just some demo to call directly tools, prompt, or resources. Now we focus on the main agent. This script primarily demonstrates how to build a client that can communicate with a server over WebSocket, leverage an LLM for natural language understanding, and dynamically use tools provided by the server. Let's dive into the code. First of all, we have some import here, and we are going to create a chat assistant class that manages all the workflow. Okay, you can see the flow here, receive the query, call tools list, ask LLM to pick a tool, in this case is text-to-SQL, and assemble its arguments. Call tools call, with choose a name and arguments, and return the tool result to the user after processed with an LLM action. So we have some parameters at the beginning. First of all, we initialize the OpenAI client. We have this connect function. This is an asynchronous method that establishes the connection to MCP server. In the headers, we apply the XAPI key. Okay, so it's necessary to interact with our MCP server. We have also the WebSocket connect here. This is the line actually where opens the WebSocket connection to the server specified by the URI, passing the authentication headers. And we pass to the chat assistant this URI. That actually is the endpoint that we create in our server, remember, is here. And using MCP is going to trigger the WebSocket endpoint and also the OpenAI key and MCP AI. And after this, we initialize the session that once connected, it calls another method that is initialize session to perform an initial handshake or set up with the server. Okay. Initialize session we can see here. And it called initialize session. That is this function here. The initial handshake with the server, with the assert self AWS WebSocket, ensure that the WebSocket connection exists before proceeding. This part, it sends an initialization message to the server. Actually, we copy the same protocol types also to the client that correspond to the same protocol types of the server. So this wrap the initialization request inside a session manage container. The session manage is likely general purpose, as we saw before. We have the model dump JSON. This Pydantic method serialized the session message object into a JSON string, which is the format for message, to send over WebSockets. Here we have the response from receive session message. It checks if the server response is indeed an initialization response, again defining protocol types. If not, it means something went wrong with the initialization and it raises an error. So we have the async receive session message. That is another private asynchronous helper. It waits to receive a raw text message, which should be a JSON from the WebSocket, return type session message, and the model validate JSON with text. Actually, it takes the received JSON string from the WebSocket and parses it into a session managed Pydantic model object. This validates the structure of the received data against the definition in protocol types. Big Y. We have call tools list. The purpose of the function is quite easy to understand. Is to ask the MCP server for a list of all the tools it currently offers. It creates a tools list request and a specific string that tells the server what kind of request this is here. And we have this while true here that it continuously receives a message until it gets the one it's looking for. This receives the message. If is instance of process update, we will see later that it receives some update from the backend. If it's an instance of tool list result, actually it receives the object that we want. This is the actual list of tools. And it return from this function. Okay. We have the call tool function. It tells the MCP server to execute a specific tool. We have the name of the tool, the method. This is the request actually. And we are going to send through the WebSocket. And similar to calls to list, it waits for the server response with a while through. And also here we can expect some process update. And if it's an instance of tool call result, it means that everything worked good and return the result. In our case, is going to be the output from the SQL query. But if it's an error, it's going to raise the specific error. We have handle user query. That this is the main public method that orchestrates. This is the most important part, actually, where you can see all the step-by-step function. It orchestrates the entire process or responding to a user natural language query. So the query is the user question. Tools, we call the tools list. Here we select the tool using the LLM with a specific prompt. We can see here. We give as parameters the query and the tools list. This is the prompt. So we're going to return only the specific tool and arguments. It also extracts the arguments. We will explain better in a few minutes. And we execute the tool and we generate the final response. So as we discussed just right now, this is actually the brain that use the OpenAI LLM to choose the appropriate tool and its arguments. It also parts here, as you can see here, this is the system prompt. All the tools that you find in the tool list, it just format in a good way for the prompt. And I call the LLM and extract the JSON and return the tool and arguments. This is the last step, the generate conversational answer. The purpose is to take the output from that tool. So it's the result of the SQL query and use the LLM to rephrase it into a natural, friendly, and helpful response for the user. And here we go. We have the main coroutine that we already discussed. And can see here, you initialize the chat assistant, you connect. After initialize, you connect, and then you invoke the handle user query, passing the user query. Actually, this is like a message from a front-end chat room. So we just need to test this system. This is the last part of this tutorial. So let's create a new terminal. We need to initialize the server. You can see all in the README file documentation how to initialize. But you can see here, we are inside the server. We are going to, first of all, we have to activate one environment Python, and we initialize with unicorn. Here we go. Okay. We have a problem because I already initialized before. So we don't need to initialize again. But I want top previous the previous process. We are going to initialize again. Okay, so let's activate. Here we go. Sorry, I'm not inside the server. Okay. I'm inside the server folder. We initialize them. Here we go. So the server, the MCP server is ready. We can now switch to the client folder and we can start main agent PY. Okay, first we also activate the vamp here. Let's see what happens. So call Python main agent dot py. Let's see. Okay, we have the process update preparing the list. We get all the list, all the tools list. The tool arguments already create the text, and here we go. We have the ensure from LLM. Sure, I found a list of people who are older than 30 years old, along with their first names. Here we go. So the system works smoothly.